Friends, types of functions. The first one, constant function. A real function f from R to R, real numbers to real number, f from R to R is said to be a constant function if f of x is equal to k for all x belongs to R, where k is any constant. For example, f of x is equal to 5, where 5 is a constant. Let me draw a graph for this. X-axis is y is equal to 0. Y is equal to 5 means 5 unit above x-axis. So that means parallel to x-axis, y is equal to 5 unit. In general, y is equal to k. Y is equal to k. So this is y is equal to k, a constant function. Observe here, this can be extended to any length. The values of x from 0 to plus infinity, 0 to minus infinity. So that means domain of the function is a real number, set of real number. Okay, and the y value is y is equal to k. K can be minus k also, so that means 5 minus 5, 10, 20 and so on. Let us write this in a set. Range of the function is k. Next, second one, identity function. A function f from a to b is said to be an identity function if f of x is equal to x for all x belongs to R. For example, f of 2 is equal to 2, f of 5 is equal to 5, f of 100 is equal to 100. Let us draw y is equal to x only. When I select x is equal to 0, y is also 0, because f of x can be denoted as y also. Y is equal to x. X equals 0, y is also 0. When x is equal to 1, y is equal to 1. When x equals 2, y is equal to 2. So similarly, x equals minus 1, y equals minus 1. See, this is the graph of y is equal to x. A straight line passing through origin is nothing but an identity function. Here we can take the values of x as 0 to infinity and 0 to minus infinity. I mean minus infinity to plus infinity. So domain, set of values of x. Domain of the function is set of real numbers, and range is, see, minus 0 to infinity, 0 to minus infinity also. You can take minus 2 means minus 2 only. So minus 100 means minus 100. So that means range of the function is also a real number, minus infinity to plus infinity. Correct enough? So then modulus function, the third type, a function f from real numbers to real numbers is said to be modulus function if f of x is equal to mod x, denoted like this, and defined as plus x if x greater or equal to 0 and minus x if x less than 0. X less than 0. Let me draw a graph of this function. X dash, y dash. When x is equal to 0, so y is also 0. Why? Because y is equal to mod x, y equals mod x, x is 0, y is also 0. When x equals 1, y is 1 only. When x is equal to 2, y is 2. Suppose if we take the negative values, x takes the value minus 1. Modulus of minus 1 means plus 1. So y takes the value plus 1. When x is minus 2, y is plus 2. So this is actually y is equal to x, whereas this is y is equal to minus x. Please observe the values of x, friends. So values of x 0 to plus infinity. So to left of the number line minus infinity. Minus infinity to plus infinity. That's why domain of the function is nothing but a real number or minus infinity to plus infinity. But observe range of the function. Range of the function. So 0 to plus infinity, including 0. There is no negative values for y. So that means including 0 up to plus infinity. Including 0 up to plus infinity. Okay. Except infinity. Including 0. We can write this as 0 plus union 0. Okay. The fourth one, greatest integer function or floor function or step function. A function f from R to R, real numbers to real numbers, is said to be greatest integer function if f of x is equal to, this is the symbol, greatest integer function for all x belongs to R, where this denotes the greatest integer less or equal to x. Less or equal to x. So that is greatest integer function of x will be when x is greater or equal to 0, between 0 and 1, so it is 0. When x takes the value less than 2, greater or equal to 1, it is 1 only. When x takes the value less than 3 and greater or equal to 2 means it is 2 only. Let me take a negative value. When I take x is greater or equal to minus 1 and less than 0, x greater or equal to minus 1, less than 0 means it is minus 1. I mean between 0 and 1, whatever the value you take, greatest integer function of that will be 0. For example, greatest integer function of 0 is 0, greatest integer function of 0.5 is 0, greatest integer function of 0.9 is 0, greatest integer function of 0.999 is also 0. Okay, between 0 and 1, whatever the value you take, fractional values, it is 0 only. Okay. So let us draw the graph of this. So let me mark the graph. When x is 0, it is 0 only. When x is 0.1, 0.1, 0, 0.9, 0, 0.99, 0, it is constant, steady. It won't attain 1. Okay. Once it reaches 1 antandre jump agate. So here, from here, so greatest integer function of 1 is 1. Greatest integer function of 1.1 is 1, 1.2 is 1, 1.999999 is also 1. Once it reaches 2, it won't attain 2 of course, so it jumps like this. So greatest integer function of 2 is 2, 2.9999, it is 2 only. Okay. So shaded region indicates including the points. So this indicates excluding that point. And even if I take x as minus 1, so this interval between minus 1 to 0, minus 1 to 0, it is this. Initial point included, whereas the terminal point is excluded. Okay. Here, like this. So this is a step function or a floor function or a greatest integer function. So f of x equals, this is the symbol, the greatest integer less or equal to x, less or equal to x. See this domain of the function. Domain means a set of values. You can take 0, 0.1, 0.99, 1.5. You can take all the real values, minus infinity to plus infinity. So domain of the function is a real number, whereas range, set of values of y, range of the function is nothing but, see, only integers, 1, 2, 3 and so on. It is nothing but integers. Correct, you know? Now, fifth one, the smallest integer function or ceiling function. A function f from a to b is said to be the smallest integer function if f of x is equal to this, okay, for all x belongs to R, where this denotes the smallest integer greater or equal to x. For example, smallest integer of 1.5 greater or equal to x means upper limit, roll forward, whereas in case of greatest integer function, roll back, so lower limit, this is the upper limit. 1.75, smallest integer function of 1.75 is 2, smallest integer function of 1.9 is also 2, minus 2.3 on the number line, so minus 2.3 means minus 2. So you are moving forward. So minus 4.5, not minus 5, it is minus 4. Whereas in case of greatest integer function, greatest integer function of minus 4.5 is minus 5, whereas smallest integer function of minus 4.5 is minus 4. Here rolled forward, whereas here rolled back, okay, on the number line. So this is the graph of the ceiling function or the smallest integer function, excluding 0, including 1, okay. So then it breaks here at all the integers. So this is excluded, included, whereas here, so initial point is included and 1 is not included. So here 1 is included, 2 is excluded, okay. Here just opposite. So this can also be, so that's why this can also be called as step function. Of course, smallest integer function or ceiling function. Sixth one, the fractional function. A function f from R to R is said to be a fractional function if f of x equals, this is how we denote the fractional function of x. We read it as fractional function of x and defined as x minus greatest integer function of x for all x belongs to R. So fractional function or decimal part of x, this is known as. Now y is equal to fractional function of x is equal to x minus greatest integer function of x. So in the closed interval minus 1 to 0, closed interval minus 1 to 0, this is nothing but greatest integer function of x is nothing but minus 1. So x minus of minus plus 1. Between this interval, including 0, excluding 1, between 0 to 0.999, whatever the value you take, greatest integer function of x will be 0. So that means x minus 0. So y equals x minus 0. In this interval, x less than 2 greater or equal to 1. So greatest integer function of 1 point something is 1. So x minus 1. So x greater or equal to 2. So less than 3. So greater than or equal to 2 means, so this greatest integer function will be 2. So y equals x minus 2. Let us take few examples. So fractional function of 2.7 is equal to 2.7 minus greatest integer function of 2.7. What is the greatest integer function of 2.7? It is nothing but 2. 2.7 minus 2 means 0.7 we are left with, which is less than 1. One more, fractional function of 6.2 is 6.2 minus 6 greatest integer function of 6.2. So 6.2 minus greatest integer function of 6.2 means 6, you know. So we are left with minus 0.2. Next, one the negative value tagolana. My fractional function of minus 2.3 is equal to minus 2.3 minus of greatest integer function of minus 2.3. Minus 2.3 greatest integer function is roll back, you know, that is minus 3. So minus 2.3 minus of minus 3 means plus 3. 3 minus 2.3, which is 0.7. One more example, fractional function of 3 is equal to 3 minus greatest integer function of 3 is also 3. 3 minus 3 is 0. So you please observe, you take any value, it is 0, 0.2, 0.7, it is not more than 1, it is equal to 0. So clearly the fractional function of x is greater than 0 or equal to 0, and here x and greatest integer function of x related like this. Obviously x is greater than or equal to, in this case equal to. So x is greater than the greatest integer function of x, and the graph is between 0 to 1, between 0 to 1, x minus 0. That means y is equal to x. Y is equal to x means a line passing through origin, you know. So including 0, excluding 1. Okay. Then between 1 to 2, including 1, excluding 2, excluding 2. So between 2 to 3, y equals x minus 2, you know, x minus 2. So cuts negative y axis at minus 2. So this is y equals x minus 2. Similarly, when I select x equals minus 1, minus 1 to 0, this is excluding actually, minus 2 to this, minus 3. So the graph is like this. See this? The maximum value of the fractional function of x will be not more than 1. So it is less than 1 only. Seventh one, Signum Function. A function f from R to R is said to be Signum Function if f of x is equal to mod x divided by x. So and is denoted like this and is defined as if x is equal to 0, x is equal to 0, 0. Modulus of x is 0. 0 by anything is 0, you know. When x is greater than 0. So greater than 0 means mod x is x, you know. X divided by x is 1. Is it not? X divided by x is 1. If x is less than 0, if x is less than 0, modulus of x will be minus x. Minus x divided by x means x gets cancelled. We are left with minus 1. We are left with minus 1. So the graph is very simple. 1, 0 and minus 1. Y is equal to 0. X equals 0 means x greater than 0 means y is equal to 1. Here 1, including 1, greater than 0 means up to plus infinity you can take. Okay. So then when less than 0 means the value of y is minus 1, including this. So this is y equals 1, y is equal to minus 1. F of x is equal to plus 1 this is. Whereas this is f of x is equal to minus 1. Here the domain of the function is x can take the value minus infinity to plus infinity. It is nothing but a real number. And the range of the function is, the values of y are 0, 1 and minus 1. Minus 1, 0, plus 1. So this is the domain of the function is clearly it is a real number minus infinity to plus infinity, and range is the set of values of y. It is including minus 1, 0 and plus 1. Only 3 values. Next, exponential function. Exponential function. A function f from R to R is said to be an exponential function if f of x is equal to a power x for all x belongs to R and a should be greater than 0. A should be greater than 0. For example, y is equal to 2 power x. A is 2. One more, y equals 5 power minus x, and y is equal to 1 by 2 the power x can be written as 2 to the power of minus 1 whole power 2x means 2 power minus 2x you can write. Next, logarithmic function. A function f from a to b is said to be logarithmic function if f of x is equal to log x to base a for all x greater than 0, a should be greater than 0 other than 1. So this is a logarithmic function. For example, f of x is equal to log of x plus 1, f of x is equal to log 3x. Nothing means the base is e, understood. You can take a can be greater than 0. E is an exponential constant. The value of e is between 2 and 3. So greater than 2 and less than 3. So this is approximately equal to 2.71. Napier's constant, John Napier exponential constant or Napier constant, different kinds of functions. So very important, please concentrate. 1 function or injective function. A function f from a to b is said to be 1 function if different elements of the set A have different images in set B. Different elements x1 and x2 are the elements. Different elements means x1 not equal to x2 implies f of x1 not equal to f of x2. F of x is image, x1 and x2 are the elements. F of x1 and f of x2 are the images. Different elements have different images. For all, x1 and x2 belongs to the set A, domain anta helತೀವಿ. For example, if the set A equals 1, 2, 3, 4 and B equals A, B, C, D, 1 associated to A, 2 associated to B, 3 associated to C, 4 associated to D, 4 mapped on to D, you can say. That is nothing but f of 1 equals A, f of 2 equals B, f of 3 equals C, f of 4 is equal to D. See, the different elements have different images, correct, that's why this is an example of 1 function. Example B, the same set 1, 2, 3, 4 and the set B is A, B, C, D. F of 1 equals B, f of 2 is C, f of 3 A, f of 4 is C. See this, it is not 1 function. Observe here, f of 2 is C, f of 4 is also C. So 2 and 4 associated to the same element. So here 1 is the pre-image of A, 2 is pre-image of B, 3 is pre-image of C, or else 4 is pre-image of D. Nothing but D is the image of 4, correct? So now 2 and 4 both associated to C. C has 2 pre-images, 2 and 4. So that's why, so different elements have different images, but same image here, not different. So this word fails, okay, definition fails. So that's why it is not 1 function. Since f of 2 is C, f of 4 is also C, f of 2 C, f of 4 is also C, but 2 and 4 are not same. F of x1 equals f of x2 implies x1 equals x2 means it is 1 function, but different elements have the same image. It should have different images. That's why it is not 1 function. If n of A is equal to m, n of B is equal to n. Cardinality of the set A, m. Cardinality of the set B is n. Then the number of 1 functions, see, number of 1 functions from set A to set B are n of b permutation n of a. This is permutation. n of b permutation n of a. If m less than n athwa equal to n. So that means the set A and B have same number of elements, or else the set A has less number of elements than the set B. So number of 1 functions will be n of b permutation n of a. You can write this as npm, npm you can write. So otherwise m greater than n means if the set A consists of more number of elements than the set B, so number of 1 functions is 0. So it cannot be 1. Next, second one, many one function. A function f from A to B is said to be many one function if two or more elements of set A have the same images in set B. Two or more elements have the same image in set B. Example, the set A consists of 1, 2, 3, 4 and set B consists of A, B, C, D. Then say this, f of 1 is D, f of 2 is B, f of 3 is B, f of 4 is A. Observe here. So f of 2 and f of 3. Right? So two elements 2 and 3 have the same image. Two or more elements of the set A, 2 and 3 elements of the set A have same image B. See this one, the second element is repeated means it is not 1, it is many one. So if it is not 1 means it is generally many one it is, since the element 2 and 3 have the same image in set B. Third one, onto function or surjective function. A function f from A to B is said to be onto function or surjective function if each and every element of set B, each and every element of the set B, each and every element of set B has at least one pre-image. Each and every element of the set B has at least one pre-image, or the entire codomain is the range. If the entire codomain is the range, that is called onto function, nothing but f of A equals B. So range of f is equal to codomain of f. To show it is onto, range of f is equal to codomain of f, or else for every element of the set B, for all y belongs to the set B, there exists x belongs to the set A such that f of x is equal to y. So this is the mathematical expression to show it is an onto function. Okay, either thus or thus. Let us take example. If A is equal to 1, 2, 3, 4 and B equals A, B, C. See, f of 1 equals A, f of 2 equals A, f of 3 equals B, f of 4 equals C. See this, each and every element associated to at least one element in the set A. So at least one pre-image in set B. That's why it is an onto function. Take this example. Here the element C, every element of the set B, but the element C is not associated to any of the elements of the set A. So that means it is not onto, since the element has no pre-image in set B. So that's why it is not onto function. Important note, as per the MCQs are concerned, if n of A is equal to n, which is greater than or equal to 2, and n of B consists of 2 elements, number of onto functions from set A to set B is equal to 2 to the power of n minus 2. 2 to the power of n minus 2. So n is nothing but n of A, number of elements in the set A. Then number 2, if n of A equals m, n of B is n, number of onto functions. Look at the condition, n greater or equal to 2, n of B 2, whereas n of B is n, n of A is m. Then the number of onto functions is nothing but n power m. Just like binomial theorem, n power m minus nc1. Difference between these two, n minus 1 the power m plus nc2, n minus 2, difference of these two, n minus 2 the power m minus nc3, difference of upper and the lower suffix, n minus 3 the power m, and so on. Fourth one, into function. A function f from A to B is said to be into function if there exists an element in set B which has no pre-image. There exists an element in B having no pre-image. That means range of f is not equal to codomain of f. The range is B comma C, whereas codomain is A, B, C, So range of f not equal to codomain of f. Such functions are called into functions. Suppose range of f equals codomain of f, that is onto function or surjective function. Example, if A equals 1, 2, 3, 4 and the set B consists of A, B, C. So f of 1 equals B, f of 2 is B, f of 3 and f of 4 both are C only, is an into function because the element A has no pre-image. That is nothing but range of f not equal to codomain of f. That's why it is into function. Observe this example. So every element of the set B associated to one of the elements of the set A. So that means it is not into function. Actually it is onto function. Okay. So if it is to be into, there exists an element in the set B. Which has no pre-image, but every element has some pre-image, So range of f equals codomain. That's why it is onto function but not into function. The fifth type, bijective function. Nothing but 1, 1 and onto function. So this is appeared in the year 2018, annual 2018 in first main. Define bijective function. Very simple. A function f from A to B is said to be bijective function if f is both 1, 1 and onto function. Let us take an example. If the set A equals 1, 2, 3, 4 and B equals A, B, C, D, then f of 1 is equal to A, f of 2 equals C, f of 3 equals D, f of 4 equals B. See, the different elements have different images. So different elements have different images. See, A, B, C, D. In the order pair, second element is not repeated. So that means it is 1, 1 function. So of course, every element of the set B has at least one pre-image in set A. Every element of the set B. Every element of the set B has at least one pre-image in set A. That means it is onto also. So since it is both 1, 1 and onto, it is a bijective function. Note, Important note as per the MCQs is concerned. So if n of a equals m, n of b is equal to n, then the number of bijective functions from a to b is equal to, if the set A consists of 4 elements, set B consists of 4 elements, m and n are equal. In that case, number of bijective functions is n factorial, that is 4 factorial. 4 factorial means 24 bijective functions, correct? Otherwise, if m and n are not equal, so there is no bijective function in such case. Type 6, composite function. If we have more than 2 sets, say A, B, C, there are 3 sets, then we come across a composite function. Okay? So let f from A to B and g another function from B to C. F is a function from A to B, function from A to B. G is another function from B to C. Then the composition of f and g is denoted like this, GOF. Composition of f and g is denoted like this and is defined as GOF from A to C. GOF from A to C. That is composition of f and g, we read it as composition of f and g is given by composition of f and g can be written as g of f of x, but f of x is equal to y, but g of y is equal to z, you know. So this is composition of f and g, GOF of the function, GOF of x, where x belongs to the set A and z belongs to set C. So this means GOF of x is equal to z. GOF of x is equal to z. Example, let A is equal to 1, 2, 3, 4 and B is equal to 5, 6, 7, 8, C is equal to 9, 10, 11, 12. So if f from A to B and g from B to C defined by, see the set A 1, 2, 3, 4, B 5, 6, 7, 8 and C 9, 10, 11, 12. F of 1 equals 6, f of 2 equals 7, even f of 3, f of 4 is equal to 8. G of 5 is equal to 10, G of 6 is also 10, G of 7 and G of 8 are 11. Then GOF from A to C is a function defined by GOF of 1, composition of f and g can be written as g of f of 1. Look at f of 1. F of 1 is equal to 6. So g of 6 is 10. Look at that. Composition of f and g. So this can be written as g of f of 2. We have f of 2 as 7. So g of 7 as 11. Then GOF of 3 can be written as g of f of 3. We have f of 3 is equal to 7 again. So g of 7 is 11 only. So GOF of 4 equals g of f of 4. F of 4 is defined as 8. So g of 8, which is again 11. So this is how composition of functions is defined.